topic of this week. We have learned the method of the lambda capacitance method since last Friday. We assume everything, the temperature distribution is uniform inside the object. And on Monday, we learned that there must be some condition for us to apply this method. Then we can get a reasonable estimation. Anyone remember we should check which condition before we apply this method? Yeah, Biot number. And it's defined as the heat transfer coefficient times some characteristic length over the thermal conductivity of the solid material. And when Biot number, which is much smaller than 1, we can assume we neglect the internal temperature gradient inside the volume and apply our lambda capacitance method with a reasonable accuracy. Let's continue the copper sphere on Wednesday. We have a copper sphere which diameter is 6 centimeters. And initially, the sphere is at 90 degrees. It is suddenly exposed to a cooler fluid of temperature which is 20 degrees. And the convection coefficient is 10 watts per square meter Kelvin. And if we would like to study the temperature profile along this line across the center of the sphere, and we mark what is our initial temperature. T naught equal 90 degrees, and the temperature of the cooler fluid, which is 20 degrees. At the very beginning of the cooling process, let's consider the center temperature. It will be a little bit cooled down, but not very much because the cooling process just starts. How about the T center for center temperature and Ts for surface temperature? Because surface is directly exposed with the fluid, and we all agree that that's the material by the last class. The surface temperature should be a little bit lower than the center temperature. Slope at the center is 0 due to the spherical symmetry. And we name the difference between delta T for inside temperature difference, which is given by the center temperature minus the surface temperature. Similarly, for the temperature difference of our spheres, of the surface temperature and the fluid temperature, we termed it as delta T out. We calculated for that's just for the initial stage of the cooling stage. How about after a period of time? Let's consider the time when the time is at some time constant after a short period of time. What will our temperature profile look like? Let's consider center temperature first. After a period of time, will it be higher or lower? Lower down than the initial state. This is some point position like here. And similarly, the surface temperature will be also further cooled by the fluid. That will be our temperature distribution after a short period of time. When after the cooling process finishes, every point inside the sphere achieves a thermal equilibrium with the fluid and should be equally at the temperature T infinity. So our temperature distribution will be just a flat straight line because everything achieves the same temperature of our the cooler fluid. Now let's pick two typical points inside our sphere. We draw our temperature distribution, which is how we at one temperature at one time, then how the temperature varies with the space. Let's consider consider surface temperature first. We draw the temperature evolution to consider at this fixed point how its temperature varies with time. Consider surface temperature first. When we draw the temperature evolution graph, we mark at the beginning everything at the initial temperature, which is T0, and at the very end, it has the same temperature of the fluid. For surface temperature, we already know, okay, when T equals 0, it's at T0. And when T tends to infinity, it's always at the temperature of the fluid. What's the shape of the curve for our surface temperature? It obeys exponential decay. Let's say by the tangent at 0, and we have some time constant. This is our surface temperature, and we have some time constant to help us to understand by which time we can consider it complete the cooling process. Then my question here, we already know the surface temperature. Where is our delta T out? Which is defined as the temperature difference between surface temperature and the temperature of the moving fluid. Right. The temperature difference with the temperature of the cooler air. And now we already get the temperature evolution for surface. How about center? How can we, based on the temperature evolution of surface, how can we build up the temperature evolution for center? For this severe case, we calculated the last class the inner temperature difference, which is given by the center temperature minus surface temperature, is more or less around 0.0525 degree. calculated this last class, and that's pretty tiny, which means for the Biot number much smaller than 1, the internal temperature gradient is negligible. How can we get, based on this, how can we draw our temperature evolution for center temperature? It should be higher than the surface, right? But as we see on these temperature distribution curves, center, because that's far from the fluid, it's always higher, a little bit higher than the surface temperature. But at the beginning, everything is the same at T0. Then at the very end, every point inside the sphere is also reaches the fluid temperature. And the blue curve is the temperature evolution for our center. And we mark the temperature difference as a delta T between those two curves. For distribution, we pick a time, then study how temperature varies for different points inside our sphere. But for temperature evolution curve, we pick a fixed position, like center, which is a blue curve, and the surface, which is our black curve here, and study how it varies with our temperature, with our time. They are equivalent, but because now as our temperature distribution has two dependence, one in the space, the radius direction, and another have a time dependence. So those two curves we should feel feel intuitive to jump between each other.